All right, so yesterday we looked at some of the thermal properties of petroleum, which ended up being kind of a bit boring. It was just like definition, 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 pretty straightforward information, but a lot of definitions there, but nothing too crazy. And a lot of the definitions explain exactly what they are, like the cloud point. This is the point. And now, again, when I say the word point, I always mean temperature. So the cloud point is the temperature when something goes cloudy. The pour point is the temperature in which something begins to not pour. It loses its ability to flow. Congealing point, the temperature where something congeals or solidifies. Freezing point, the temperature at which a liquid becomes solid, very similar to congealing point. Volatility is how easily a substance turns into a gas, which brings us to the flash point, which is the lowest temperature possible in which a chemical will catch on fire. Which brings us to a safety thing, wink, wink, kind of important to know. When a fuel or chemical has a low flash point, so the temperature it can ignite is lower than about 40 degrees Celsius, we call that a flammable chemical. So it's a safety hazard. And then we had specific heat and latent heat. These are related to the amount of heat something can absorb, and in particular, the latent heat of vaporization is the amount of energy something can absorb to turn into a gas. So all pretty easy definitions. I just very quickly explain them all in, I don't know, 2 minutes. So let's get into this section. I would love to finish this today, this section, and then that'll get us ready tomorrow to get into the section that your lab will be on. Okay, so physical properties of petroleum. Remember what physical properties mean. They are definitely related to thermal properties. So this is like the other properties besides heat-related ones. So physical properties besides, melting point and boiling point would include things like density, viscosity. What else are we going to talk about in here? Viscosity, surface tension, and really that's about it. So it's a pretty quick little class today, I think. All right, so the API density. Now, unfortunately for the rest of the world, the oil and gas industry still uses a lot of American standards and even American numbers. What I mean by that is, when you it might be different in the Middle East actually, because I've never really worked in oil and gas here, but I know in Canada, just like Qatar, we're a country that uses the metric system. So we would use kPa for pressure, and we would use meters and kilograms. Well, I know the oil and gas industry back in Canada is a little heavily dependent on America or the United States. So we use things like PSI for pressure, pounds per square inch. And another unit or physical property that we use is from the American Petroleum Institute, the API gravity. So obviously that is API acronym or initialism, I think it's called. It stands for American Petroleum Institute. Really easy concept, but a little bit backwards because it's American. So the API gravity is how heavy or light a petroleum is, like a petroleum liquid, a oil and gas liquid, compared to water. So this is where it gets confusing because the Americans like to make things confusing. If the API gravity is bigger than 10, it's lighter than water and it would float on water. If the API density is less than 10, it's heavier and it sinks. Now, just take a minute to like just think about how confusing that is. In chemistry or physics, if something has a higher density than water, it will sink. Okay. Well, I mean, the same is true for oil and gas, for petroleum liquids. If the density is greater than water, like the actual density, it would sink. But API, for some reason, I'm shaking my head right now, but they use the number 10 as a baseline. And if that gravity or density for their measurement is bigger than 10, it would float on water. And if it's less, it sinks. It's kind of a reverse. Yeah. Like Saif in the chat, you're laughing and I'm laughing too. It makes no sense. I'm sure maybe if I could talk to like an American petroleum scientist or chemical engineer, they might give me a better reason, but it just seems backwards. It seems so backwards. So if the American Petroleum Institute density or gravity, they mean the same thing. In physics, they call it specific gravity. We would call it density in chemistry. But if it's bigger than the number 10, it floats on water. Less than 10, it sinks in water. This could mean a bit for environmental cleanup, for example. Oil spills that float on water can be, very dangerous or harmful to the environment. But the fact that they float means you can clean them up a little easier. And you guys should have done a course by now. Have you ever done a course, EN? I'm trying to think of the number. I taught it one time, like a million years ago. EN something something, like 27 something. It's a kind of an environmental course, but in that course you look at cleaning up oil spills. Not really relevant to this, but anyways. So the API gravity, again, that's just density. Let me just check the chat here. Yeah, EN 2480, that sounds really familiar. Years ago, 8 years ago, or maybe 7.5 years ago, it was one of my first semesters here, and they really needed some help in engineering. So I taught that course and another chemical process course. I think it was CH2420 or 2430. Very cool course, that one. Anyways, so API gravity is commonly used around the world as an index. This is, a number, a reference, sorry, for the density of a crude oil or refined products. So yeah, you can think of index like reference. It's the industry organization that created this, so it is used in different places in the world, even outside of the United States. API is calculated using the specific gravity and then this formula here. Now, you do not need to memorize this, and we will not be doing this calculation in this course. The course outlines don't ask us to actually calculate this. We just need to know what it is, and you don't need to even memorize that formula. But the formula is you take a number, 141.5, you divide it by the densities or specific gravity of the chemical, of the hydrocarbon, and then you subtract 131.5. No idea where that formula came from. Some crazy American mad scientists came up with it, but there we go. And you do not need to memorize it. So this is why this is confusing. And we can thank the United States for this. The API density or gravity is an inverse. It's opposite of what we think, which just breaks my little chemistry heart. I don't know why they do this, but it's an inverse measure of the petroleum's density compared to water. Relative meaning compared. So what's the point? Okay, I've been kind of going on a rant about it, but what's the point? It's just a way to compare densities of petroleum liquids. Okay, how dense they are. Now, in crude oil or something like that, these are obviously mixed together. We have nonpolar substances that form a mixture, a miscible solution, well, somewhat miscible solution. So it's a little harder to, pick apart their densities. But when you mix something like a petroleum product with water, ones that are more dense will sink, ones that are less dense will float. So a crude oil, now again, this is the interesting part about crude oil. It changes wherever you are. So, the crude oil that we find in the Middle East is very different than, say, Northern America or Northern Canada. But typically, you can find them between 15 and 45. They use the unit degrees, but 15 and 45. These numbers, because they're greater than 10, will float on water. So there's obviously then not many crude oil products that are less than 10, meaning they would sink in water. Most crude oils in the world would float on water. Generally, the bigger the number, I think maybe this is where the Americans are going with this. The higher the number, the better it is, the more value. And that's, if you're thinking, maybe I shouldn't say this because I'm going to be on YouTube, but if you think about an American way to define something, it would be based on its value, right? And the higher the API density, the lighter it is. The lighter it is, the more valuable it is. So that's probably likely where the Americans came up with that number or this concept. So this is a pretty, well, not that old. This graph is about 4 years old, maybe 3 years old. And it shows now, this is the best I could find. I couldn't find a very good global one. This is the lower 48 states. So this is everything in the United States, I guess, except for Alaska and Hawaii, I guess. But this is the distribution of oil based on their gravity or density for 2015 and 16. And you can see it almost looks like a bell curve you would learn in math, right? But you could see most of that crude oil is between, let's say, 35 and 45. I wonder if I did a quick search. I don't know if I'll find anything. There are some things like I'm looking at QP, Qatar Petroleum's marketing site, and they have a really interesting PDF here that looks at some of their marine crude oil. And the gravity, the API gravity of this product, I'll send this to you guys in the chat if you want to open it, is between 32 and 31. So pretty valuable, pretty good result there. This is marine or offshore oil. This chart actually also tells us the acid number and the pour point, which we learned in the last section. And it also talks about the wax content, which would affect the congealing point. Let me just send that to you guys. Hold on, I got to get rid of my screen share for 1 second. I'm just going to send you that because it is kind of a little interesting document. It was published, it doesn't say when it was published, but it's probably pretty recently. So hold on, let me share that with you. You don't have to open it. You don't even have to read it. But if you're curious, it can be cool. It kind of shows some physical properties of the crude oil found offshore in Qatar. This would likely be very different, or maybe not very different, but somewhat different than the crude oil found in like the UAE or Saudi Arabia or wherever in the, around the Gulf here. So let me put this in the chat. This is a PDF. So there you go. That's from QP, and it mentions that the API density is around 31 to 32 for their sample of marine crude oil. Okay. All right, let me get back to this. Share. Okay. So, okay, what do you need to know? Right? This is a lot of information, but what's important really, there's two things you should know, two and a half things you should know. API density comes from the American Petroleum Institute. The density is related to water, and the higher the number, the less dense it is, meaning it's more valuable in refining. Okay, or for refining, I should say, not in refining, for refining. So API is an American kind of unit for density or gravity. It's compared to water, and the higher it is, the less dense it is, meaning it's more valuable. Cool. All right, that's it. That's it for API density. So I'll talk about temperature and viscosity and hopefully get into surface tension. We'll see how much time I have, and that'll be it for today. This concept of surface tension is one of my favorite things in all of science, and we will learn more about it tomorrow in this section, which is maybe my favorite section in any chemistry course I've ever taught, and I've taught maybe 10 chemistry courses, so I love the next section. I cannot wait to talk about it tomorrow. So let's get there. Interesting fact about density. Density is affected by temperature. Okay, so typically the higher the temperature, the lower the density. You're like, think about what temperature is and think about what density is. So temperature is the kinetic energy, the movement of the molecules in a compound. Density is the grams of that compound in a specific volume, could be liters or milliliters, typically. Well, as you heat something up, you're making the molecules move more. That's what temperature is, right? The kinetic energy, they're moving more. When they're moving more, the space between them can get a little larger. So for almost any chemical that I can think of, when you increase temperature, when you heat up a liquid, the density decreases. You're increasing the space between the molecules. So this is true for mostly water. Water has a few weird exceptions, but this is true for most chemicals, and hydrocarbons or crude oil specifically is one of them. It's true. So crude oil densities and temperatures are found used on standards from the API manual, which I got from this site. You obviously do not have to memorize this, but it's good to know that as temperature of anything increases, the density typically decreases. And specifically, as the as the temperature of crude oil increases, its density will decrease. Now, viscosity and kinematic viscosity. Really, in 2420, we would be more concerned with just viscosity. So what is viscosity? And I've talked about this before. Most of you guys already know what this is. It's the fancy definition is it's a fluid's resistance to flow or resistance to deformation is what my slide says. So it's the thickness of that liquid. All right, now thickness, that's a subjective term. What do I mean by thickness? I don't mean thick like as in length times width times height, like, or, I don't mean a volume. Thickness, I mean like its ability to pour, P-O-U-R. Ability to pour. Okay, now, easiest example, I've been basically using this example since I can remember. Compare honey or something like maple syrup, but honey is probably a better example for the Middle East compared to water. If you put honey in a jar and water in a jar or a cup and you poured them out, well, the water would pour out much quicker. And again, this would be important that they were at the same temperature. If you ever have like honey stuck inside of a bottle and you want to use it, like you're cooking, easiest way to get the honey out, put it in the microwave or put the bottle in a microwave or put the bottle in some hot water, and by heating it up we decrease the viscosity, we make it less thick. Kinematic viscosity is obviously directly related to this. The fancy word is momentum diffusivity, but this is the relationship of the viscosity to the density. And just remember, there are no calculations in this course, so you don't need to know this. There are no calculations in this course, but there's a unit sometimes people use where it's the ratio of viscosity, which we use mu in chemistry, and the density, which we use rho. You do not need to know that, don't worry. So viscosity is the thickness of a liquid. If something is viscous, it's thick. Now, wink, 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 wink. What are some factors specifically for crude oil? What are some factors that would affect the thickness of something? Well, and more specifically, I mean, what are the principal factors that would affect the thickness of oil and gas, or I guess I should say crude oil, not oil and gas, crude oil? Well, there's four things. Let me skip the first one for a second. Temperature. Temperature affects flow rate. If something is warmer, it will flow better. So one of the factors that affects the viscosity of crude oil is the temperature. And again, you can think about working in like northern Russia or northern Canada, where it can be -30, -40 degrees Celsius, versus working in the Middle East, where it's typically +30 or +40 degrees Celsius. Oils will be more viscous in cold temperatures. They'll be thicker. Another factor that affects the flow rate is the amount of dissolved gas. Typically, if something has a lot of dissolved gas in it, it would be a little lighter and flow a little faster. Now, I don't mean like a foam where it has so much gas it's foamy, but typically something with more gas in it would flow a little better. Remember, gases have high kinetic energy. A dissolved gas would kind of lighten the liquid or solution and allow it to flow a little better. Pressure. Pressure definitely affects viscosity. Pressure is the force on an object. So if you're pumping crude oil through a pipeline at high pressure, it's going to flow a lot better than something at low pressure. Let me give you an example. Take a plastic bottle of honey. Now, I'm cheap. I always like the Middle East has some of the best honey I've ever had in the world. Well, certainly the best honey I've had in my life, I should say. Back home, we just use kind of like cheap, uh, large manufactured honey, and it comes in a plastic bottle. And typically, that plastic bottle is shaped like a little bear, like Winnie the Pooh. So it's kind of silly back home, but it comes in a little plastic bottle shaped like a bear. And I'm thinking about how pressure affects the viscosity of that honey, the flow rate. When I take that bottle of honey, and you can think of any bottle, could be ketchup, mustard, mayonnaise, whatever bottle you have, tip it upside down and wait. And eventually some of that might flow out. Like honey, it would definitely flow out in a minute or two. But now think about that same bottle when you squeeze it. Pressure is just squeezing. Oh man, my pen. Pressure is just squeezing an object. So when you squeeze something, that's a weird word to spell. Squeeze. I don't even know if that's right. It looks right. When you squeeze something, you're increasing the pressure, so it would flow a little faster. And this really relates to oil and gas when you're talking about pipelines. The pressure in a pipeline affects the viscosity. And then the last factor, I did the bottom three first, is just what is the oil? What is it made out of? Does it have a lot of asphaltics, which would typically be thicker, more dense, or is it a lighter oil composition? Is it made of things like short chain alkanes or alkenes? So wink, 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 wink. These are four factors that would affect viscosity. What is the oil made of? What is the temperature? What is the pressure? And is there a lot of dissolved gas in that chemical or in that crude oil? All right. Okay. Fluidity, guys, you do not need to know this. This is in your outcomes. Fluidity is the reciprocal. So reciprocal kind of means flip in math. Um, this is in the outcomes in your course, but from my research, fluidity is seldom used in engineering practice, and there are no calculations in this course. So we can ignore fluidity. It is in your notes. You might hear about it someday. It is the inverse of viscosity. But don't worry, you don't need to know fluidity. So I'm going to go on. I'll do two more slides on viscosity, and then I'll quickly get into surface tension, and we're done. I hope everybody's doing okay. I know this is a little boring compared to chapters 1, 2, 3, and 4, where we had to do lots of naming and reactions, but it's kind of interesting. Okay, so viscosity in oil. A very common occurrence in the oil and gas industry is a two-phase flow in your pipeline. Now, what does that mean? And I should say this is common in the petroleum industry, but other industries as well. Chemical, geothermal, even nuclear, which I don't know too much about. So what is a two-phase flow? Well, it's when you see a mixture of gases and liquids. Okay, we'll talk more about what that type of mixture is in the next section, but a gas and liquid two-phase flow happens in a lot of industries. So what I mean is the liquid that you're putting through a pipe has dissolved gas. If you don't know what dissolved gas is, that's fine, but every one of you has experience with dissolved gas because I'm sure at some point in your life you drank Pepsi or sparkling water or Coke or something. That's dissolved gas. It's when you take a liquid, so like Pepsi or Coke is just sugar water basically, with coloring, and then they put carbon dioxide into that. So that would be a two-phase chemical. There's dissolved gas in that liquid. So when you're looking at oil flow, it's important to kind of consider this mixture of gas and liquid. And it's also really important to try to predict the flow pattern if you're going to see any pressure drops or liquid holdups when you're looking at producing or transporting crude oil. Anything that disrupts flow can cause a problem. It can clog a pipe, it can cause a backup, it can make an oil spill happen. So really anything that can slow or stop flow can cause huge problems. You can think of it like a traffic jam. Now, I gotta say, and I don't know if you guys agree with me, COVID aside, I found in the last 8 years I've been here that the traffic in Qatar has been amazing. Has been getting better. Not amazing. It's definitely not amazing, but it's definitely getting better. I remember 8 years ago, the traffic on the expressway, the D ring, used to take me an hour to get to work. Now, I don't live in the same place anymore, but I find the expressway a little less congested, especially with all the work they're doing. So all of that construction that they're doing on the roads, even the metro and trams and flyovers, that's to help the flow. And cars on a highway, that's just like oil in a pipeline. And if you have a traffic jam, it can cause problems. There can be accidents, braking. People get really mad. It costs people money. So you can kind of think of like oil flow in a pipeline like a highway or an expressway. And if you can have consistent and safe flow, it will save you time and money. So here's the problem. Almost all flow models have viscosity. Well, sorry, I shouldn't say here's the problem. Here's the thing. Any flow model that a chemical engineer would look at when you look at fluidity and flow rates would consider viscosity or thickness of that oil. So intrinsic meaning this is a variable they need to consider when you're talking about the flow rate of oil. And two-phase flows, which is definitely beyond the scope of this course, but when you're looking at an oil and gas mixture, they have different behavior than higher viscosity oils. So you don't need to remember anything like this specifically, but just know that it is a challenge for chemical engineers to make flow models or to study or predict flow rates with oil and gas without considering viscosity. Okay, I don't know. Well, I probably might get this finished. What I might do is just kind of talk about this quickly. And these four slides directly link into my favorite section. So maybe what I'll do, because it's 10:15 almost, is I'll introduce this and then we'll kind of do a review of surface tension tomorrow and get into my favorite chapter, section 5.13. Love this chapter. And this is again what your lab number 6 will be on. So once I get that video uploaded, it'll be on this chapter. Really fun experiment. All right, so surface tension. Ooh, I love surface tension. It's useful in cooking and a lot of natural sciences because it directly relates to water, which has a very high surface tension. So what is surface tension? It's actually interesting, and it can be very complex when you try to mathematically explain this, but it's the tendency, it's the behavior of the surfaces of fluids to try to shrink into the minimal possible surface area. This has to do with intermolecular forces, so like how these molecules are attracted to each other. But surface tension is one of the really interesting properties of water, which allows it to form droplets or beads sometimes on things like a waxy leaf. If you guys want to see surface tension right now in your kitchen, you can do it after. Well, let me do this and then we'll kind of stop for today. If you guys want to see the amazing surface tension of water, you can do this right now if you're home in your kitchen. And if you're not home, you can do this later. It's really easy. So take a glass of, well, take a glass, not a glass of anything, but just a regular glass. Okay, so that would be my glass. I'll do it so we're looking onto it straight on by its side. And start to fill the glass up with water. So pour your water in. And once it gets to the top, very, very, very slowly add more water. Now, most solutions that have lower surface tension or lower intermolecular forces would kind of level off, right? And any more water you poured into it would just go over the edge, or sorry, any more liquid. But if you're careful enough with water, you can actually see this happen. And this doesn't happen with every chemical, but it certainly happens with water. It will actually form a small dome over the top of the glass of water before it starts to pour over the edge. And that's because the water has high surface tension. The surface of the water is tightly is tight and it's attracted to each other. So rather than break and pour over the edge, just for a little bit, it will form a dome. Now, if you add too much water here, like it would never be infinite, meaning you wouldn't get a dome that looks like that. But, you'll get a little small dome. And if you add any more water, it will fall over the side. So that's related to surface tension. And the definition of this is crazy, but we'll look at this tomorrow because it's 10:16 and I think that's enough. So tomorrow, I'll explain a little bit more about surface tension, and that will bring us into this because this is all about surface tension. All right, guys, if you have any questions, let me know. Other than that, I'm done for today. So I'll see you all tomorrow in class. Have a great day. And like I said, if you have any questions, let me know.